my name is George Fritz, and today we're going to be talking about bomb calorimetry and the multiple means by which we can determine the resonance energy of benzene. But first, I think it's important we discuss what the actual resonance energy of benzene is. According to thermodynamics, the internal intrinsic energy of molecules is derived from the energy of the atoms bonded to one another. In this circumstance, benzene has 6 carbon-carbon bonds, including 3 double bonds and 3 single bonds, and also 6 carbon-hydrogen bonds. Therefore, it would make sense that if we took a molecule such as CDDT, which has 12 carbon-carbon bonds and 18 carbon-hydrogen bonds, and subtracted out the energy of the bonds seen in cyclohexane, we would be left with the exact internal energy of benzene. Let me try this really quick. Oh wait, benzene is something special, a thing that every OChem 1 student could never even imagine is real. I have a feeling that benzene might just have more energy than the difference of CDDT and cyclohexane. But why? The answer lies within resonance. Due to benzene's delocalized pi electrons contained in its 3 double bonds along its rigid cyclic aromatic ring, surely its energy cannot just be the sum of 6 carbon-hydrogen bonds and 6 carbon-carbon bonds. The extra icing on top must be its resonance, which serves to increase the internal energy of the system. But how to determine it? I got a C in PChem. I wouldn't want this idea, which could lead me to fame and fortune, to just blow up in my face. That's it. Let us use the isodesmic reaction of benzene and cyclohexane as a starting point. If I can find the enthalpy of combustion of all these species, surely I must be close. I knew that bomb calorimeter would come in handy, but I would need to have them all in the same state of matter to put them into their corresponding equations before I could actually do it. Eureka! I have an idea. 6 equations, 3 being the phase changes, which give me the enthalpy of vaporization in gaseous phase, and 3 being the combustion reactions, which will help me determine the enthalpy of combustion. All these are crucial to helping me understand the internal energy change of my liquid samples and examine them in the gaseous phase. But I don't really want to touch any benzene. I heard that's how Dave Waldeck started hearing things. But how will I find the enthalpy of combustion for that? I know. I know what I'll do for finding the enthalpy of combustion for benzene. I'll do what any self-respecting PChem student would do. I'll just Google it. But what's the point of all this anyway? Wait, I could save the world. Bomb calorimetry is used in so many applications, whether it's determining the energy of new biofuels, determining the energy of feed pellets for livestock, or finding the calorie content of food just so they can put a small print at the bottom of the Applebee's menu for everybody to ignore. Yeah, it's exactly worth it. All right, let's come up with some hypotheses. My favorite 2 points to lose in my pre-lab. First, I want to test these claims using my favorite chemistry computational software, Cygress. It's extremely user-friendly and always works flawlessly. I'll manipulate Cygress to first examine all conformations of CDDT at 298 Kelvin and use the lowest energy one to find the most common one that will be in the delta H of combustion. Once I repeat the same for cyclohexane, I'll use its delta H of combustion to find the resonance energy of benzene. Perfect. First, I expect the computational data will give me a lower enthalpy of combustion for CDDT. This is because we'll analyze it at one conformation. However, in solution, it could have a variety of conformations. This means that some will be higher and some will be lower, but considering the distribution of 298 Kelvin in the Maxwell-Boltzmann distribution, I see it possible that most will be higher. Secondly, the enthalpy of combustion for CDDT will surely be higher than that of cyclohexane. The greater number of bonds means greater internal energy and hence a greater change in enthalpy upon combustion. All right. Let's get the calorimeter set up, and as Tyler Perrick says, let's do some science. My bomb calorimeter consists of a bucket of water with a closed metal bomb inside. Inside the bomb, there's my CDDT and my sample basket, or my cyclohexane, connected to a short length of wire inside the bomb itself. Outside the bomb is the water, a motorized water agitator, and a thermometer. These will help absorb the heat from combustion so that I can track the temperature over time. Once I flush the system with oxygen and pressurize the bomb at 30 atm, I think it'll be ready to go and I'll ignite it. All right, time to wait 3 hours and 50 minutes. Okay. It worked. Oh no, my air propagation machine. How will I propagate air? I'll have to figure out some way. Okay, now that I have 6 graphs of temperature data per time, I can use this baseline correction equation shown above to determine the accurate temperature change. This requires 6 data points and the slopes of each of the horizontal places in the graph for peak accuracy. So here are my 6 graphs, 3 for CDDT and 3 for cyclohexane, and their corresponding changes in temperature can be seen on the right. To determine the enthalpy of combustion, we must first start with the heat. This is determined by multiplying the change in temperature by delta T. The heat capacity of the bomb is the letter C here. To determine and account for the extra fuse wire, or in the case of cyclohexane, and also the capsule it's placed in, we must subtract out the necessary heats which correspond to the burned portions of the irrelevant garbage contributing to the total heat. This heat is exactly the internal energy of combustion in joules. Once I divide through the moles of my sample, the proper units for delta U, the internal energy, can be determined from the Q, which is the heat of the sample. Okay, now that we know the enthalpy of combustion, delta H is equal to the internal energy plus the change in N, which is moles in gas, which is change in moles of gas, times the gas constant R at room temperature, which was 298 K. Change in moles of gas can be found by finding the difference between the products and reactants on both sides of the gas molecules from the balanced equation shown before. These lead to the results shown below. You can see that CDDT actually turned out to be more than double on average the heat of combustion per mole of cyclohexane. But there's an outlier we may need to consider. You know what outliers do to our results. Oh boy. All right, so now we have the enthalpies of combustion. Using the data from Maher and Swoboda, I used the Clausius-Clapeyron equation to determine the enthalpy of vaporization of CDDT. Using the slope of the graph and multiplying it by the gas constant R, it was determined to be 47,674 joules per mole. Now that we have that value, and the rest we can find using our best friend, Google Scholar. All these literature values will be important to helping us determine the resonance energy of benzene. All right, perfect. We have everything we need. Let's crunch the numbers for real this time. We find the resonance energy of benzene to be 2,361.43 kilojoules per mole. Or if we exclude the outlier, it'll be a much lower 101.13 kilojoules per mole. Additionally, my beloved Sigres came to the value of 138.26 kilojoules per mole by simply subtracting delta H of products minus reactants for the isodesmic reaction. So now we can compare results. The outlier considered, the experimental value is far greater than the computational value, with a huge error of 1,604%. There were evidently large issues with the experimental technique, which I'll address. However, let's first consider some of our hypotheses. Hypothesis 2 can be evidently accepted, as the average enthalpy of combustion of cyclohexane was smaller than that of CDDT in terms of magnitude. This helps demonstrate the validity of the theory that larger molecules result in larger changes in temperature. Additionally, we can accept hypothesis 2, which states that the computational value would be smaller than the experimental value for the resonance energy of benzene. Looks good, considering, as you can see below. But considering other factors, it's extremely difficult to measure quantities such as the small resonance energy of benzene without extremely accurate measurements of enthalpy of combustion for these larger molecules, which are comparably massive in comparison to the resonance energy of benzene. It's apparent that the larger the molecule, the larger the variability in terms of delta H measurements. For example, both excluding and including the outlier, the standard deviation of delta H was larger for CDDT by orders of magnitude in comparison to cyclohexane. Overall, a variety of human error and systematic error could have contributed to these problems. However, for future experimentation, systematic error would be most important. These possibilities include sample loss due to vaporization, which may have resulted in a lower delta T for liquid samples. Heat loss is also a very real possibility, as heat can diffuse outside of the conductive surface of the bucket into the atmosphere undetected by the thermometer. Although difficult, this is unfortunately not a measurement which can be done using just benzene alone, as bond enthalpy calculations alone cannot tell us about the stabilizing nature of aromatic rings. Although they tell us about the intrinsic energy of a molecule, aromatic rings tend to stabilize molecules in ways that we can't measure just mathematically. Okay, so how are we going to improve everything? Results can be improved by more rapidly mixing water to ensure it reaches the temperature probe during the measuring period. It could also include taking more data points to minimize the effect of random error in data. If you took more points, you could work to create a better average value. And additionally, performing the experiments at varying quantities could help, or using different molecules, which we'll talk about in the future. A more tightly insulated container could also prevent heat loss, which would be important to accurately determine delta T. Regarding other molecules, cyclooctatetraene could be very valuable. This molecule, because it is not aromatic, could be analyzed in the same way as benzene. Subtracting delta H of ethylene minus delta H of the ring could provide another way to learn about the resonance energy of benzene. Also, because it only exists in one conformation, it would have a lot less variability. Additionally, data from heat of hydrogenation could also be used to determine the resonance energy. For example, by hydrogenating cyclohexene, the heat of hydrogenation could be detected, then performing the same for benzene, three times the cyclohexene value, which would emulate the molecule cyclohexatriene, could be subtracted from the benzene quantity to determine the resonance energy. This shows that the effects of resonance from pure double bond hydrogenation enthalpies can be used directly to determine E resonance. This, however, brings about the question as to why benzene has such a high resonance energy, and the answer lies in the structure of its pi system. Benzene in particular is specifically resonant because of just how small it is, and it follows Huckel's rule as it is high aromaticity, which is very stabilizing. The pi cloud's significant overlap helps ensure aromaticity, which cannot be seen within these other molecules, which have less overlap, especially in the linear molecule. Overall, this shows that bond and molecular energy should not solely be determined by one technique. Future research will be needed. Additionally, enthalpy of combustion is not the best practice for maybe finding small differences such as E resonance. The complexities of these measurements require better methods in general.